He only had part of it. So he probably would have only been able to partially
go back home.
Should throw it at him. That would probably hurt. It was.
He probably has the rest of gun back home.
Yeah. Anyways, so Steve has n shoes in a statement which is true or false depending on that number n. Steve has 15 shoes. Probably true. I'm a rock climber. I have lots of pairs of shoes. Like
but
lots
you
of
only have half a pair?
Yeah, because like sometimes you need just a shoe for one foot for a specific movement. Yeah. But I mean, Steve has one shoe is true. I have one shoe. I also have two shoes. That's also true. So it would be true up to a point. But then Steve has 1 billion shoes. Probably false-ish. Right? Speaking of rock climbing, if anybody wants to go to a rock climbing competition in Arkansas this weekend, you should. Elevate Rock Gym or Elevate Movement Sports. It's my friend's gym. They're throwing a rock comp. So this is how we evaluate P of n. Now I want to talk about mathematical induction, which is going to cover the rest of this stuff. And we're going to use P of n pretty loosely and frequently. So are there any questions about how P of n works? Do you see any more examples? I think it's pretty clear. Okay. So mathematical induction, I'm just going to give you, kind of like here, I didn't define P of n, I just gave you an example. I'm going to give you an example of a proof by induction. So I'm going to give you this proof by induction. I'm going to label the anatomy as I go, and then we'll use that to define these things rather than a formal definition. I have a formal definition typed up in my notes, and it's just wretched. Let me look at it. Yeah, it's just a nasty paragraph. I think I prefer to just do an example. So prove that for all n natural, the sum as j goes from 1 up to n of j is equal to n times n plus 1 divided by 2. Now, poor Colton, poor Jiangfeng, in my calculus class, we just talked about this last night. Sorry guys. Or not last night, Tuesday night. Remember, how many different ways did I prove it? Did I prove this 2 ways in calculus? Right? We summed up the squares, and then, yeah. Okay, this is yet another way to prove this. It's great. There are lots of different ways to prove this. So let's prove this. Here's what I'm going to do. I'm going to define this whole thing as a statement, P of n. Okay? Suppose I gave you some formula involving n, some equation involving n, and I said, this equation is true for n is my P of n. So any value of n for which this equation holds will give me P of n is true. Any value of n for which this equation does not hold will give me P of n is false. Okay? So my goal is to show P of n is true for all n in n. This is what I'm going to do. All right? So this is a proof by mathematical induction. Again, like I said, I'm not actually defining this. I'm just going to do an example, break down the anatomy of the example, and then hopefully that'll be enough of a definition. To do mathematical induction, what I want to do, it's kind of like a recursive function. I want to have a base case and an inductive step. That's like how when we define a recursive function, we have a base case and a recursive case, right? We have if my input is some empty string, that's my base case, I do nothing. If my input is not an empty string, that's my recursive case, I do something, right? So we're going to start with the base case. Which I'll typically abbreviate BC. This is typically a small value of n. It's P of n for typically a small value of n. So we're going to show P of 1. Now, if you study mathematical induction, and I think that a lot of you probably should, it's really beautiful and really powerful. Everything can be boiled down, like via logic, to a statement like this. Ish. That might be too strong of a statement. But the point is, there are a lot of different ways to do mathematical induction. You're going to see strong mathematical induction, weak mathematical induction, they're equivalent, but they just sort of look different. I'm going to show you just the most basic way to do mathematical induction. There are all sorts of powerful inductive arguments. We're going to just do this most basic one. But you're typically going to start with a small value of n. Now, since I'm saying let's do this for all n natural, what's the smallest natural number? It's 1, okay? Sometimes I'll say, prove it's true for all non-negative integers, and then we might start at 0. But here we're going to start at 1. So let's write down P of 1. P of 1 says, as j goes from 1 up to n equals 1 of j, that has to equal 1 times 1 plus 1 divided by 2. And 1 does equal 1, so we're good. Okay, we just showed, so P of 1 is true. I guess I should write that. Typically, in an induction argument that I give you in this class, the base case will be pretty straightforward. So typically this first step will be pretty straightforward. You just kind of have to pick a small number, and you can typically verify it. All right, the sum of all the integers ranging between 1 and 1 of those integers is just 1. It's a for loop that only executes once. Okay, for I equals 1 all the way up to 1. Okay. The right-hand side, 1 times 1 plus 1. Whoops, tricky. That's 1 times 2 divided by 2, also 1. So we just verified their equivalence, right? Okay, now, the inductive hypothesis also known as IH, is just a restatement of Pn. So I'm going to write it down again. You don't have to, but it's just that the sum as j goes from 1 up to n of j is equal to n times n plus 1 over 2. The inductive step is showing P of n implies P of n plus 1. Okay, I have to be careful now. P of n is a statement. You can also think of it as a Boolean function. Wait, is this too small? Guys, is this too small back there? Can you read that? Okay. If Daniel can read it, I'm assuming anybody can read it because he's the farthest point. All right. This is is not a f maps something onto something else. So don't confuse it for that right arrow. This is saying if I have P of n is true, then it logically implies P of n plus 1. All right? Cool? P of n implies P of n plus 1. That's what I want to show. What's P of n? P of n is a statement, some statement, it happens to be mathematical, but it's some logical statement that involves n for whatever reason. Okay? The inductive step is taking this statement, manipulating it, doing awful things to it, and somehow using it to prove that the same statement is true for the value n plus 1. This is typically where the work is involved in an inductive problem in this class. I should mention, you don't have to say mathematical induction every time. It's just, for starters, I'm introducing this as mathematical induction so you don't confuse it with, the relationships between, current and magnetic flux, things like that, okay? We're not doing, B dot loops or, oh, Ia's not here. I make jokes about partial differential equations. Let's just pretend I made a really funny joke. Everybody have a chuckle and be like, haha, Ia didn't get to hear it. It's really funny though. Yeah, what's up?
Just a notation question. Is there a difference between the double arrow and the single arrow?
That is a really good question. So, I use the double arrow when I am speaking with authority. So, if I'm in the middle of a proof, I'm telling you this implies that, sort of a higher level of scope, right? It's actually the same thing, but I write it like this so I don't have to put parentheses around everything. So when I'm saying this, what I'm actually saying is the statement m divides c times a minus b implies there exists an integer k such that blah, blah, blah. This is what I'm actually saying. And I think I mentioned this earlier, but I might not have been super clear about it. When I have a double arrow, I mean this chunk implies that chunk, and I'm not gonna, hopefully it makes sense. Or I like to use it between lines. Like I would say, yeah, like you might see me as I'm working on proof, write a double arrow right there, or something like that. This is me sort of outside the system saying that, as opposed to working within the system, where here, this is the statement that I'm manipulating. So this is like part of the statement. Does that make sense?
Yeah.
It's really not carefully defined. I don't make a very careful distinction, and I do apologize for that. But this is just the kind of how we do things in mathematics. Is we frequently use this if I'm talking about this statement, and I'll use the double arrow as like part of a proof or part of a procedure. That's just higher level of organization. Yeah. Okay. Yeah, I think I briefly mentioned that the very first time that you saw this, I said like sometimes I use double arrows, but I don't think I ever made the explicit distinction. Here's how you can separate the double arrows. Oops. Thank you for asking. I appreciate that. I apologize, guys. I should have explained that more clearly. So the inductive step is showing that P of n implies P of n plus 1. So what I am going to do is I'm going to write P of n here, and then I'm going to use the double arrow to get us to P of n plus 1. That's like part of the exposition. Here's me. This is like me telling you a story. Here's what I'm going to do. I'm going to walk over there, I'm going to pick up my phone, and then this is going to be me actually walking over here and picking my phone, okay? So I want to start with P of n. P of n is, and I'm writing it yet again, because I can't get enough of writing. The sum as j goes from 1 to n of j is equal to n times n plus 1 over 2. Now, we're going to get a little bit meta. I'm going to need to think about what P of n plus 1 will look like. So I've got a goal. I want to get to this statement, but with an n plus 1 everywhere there's an n. So let's just talk about what's our goal. What are we shooting for? We're shooting for the sum as j goes from 1 up to n plus 1 instead of just n. And we're shooting for n plus 1 times n plus 1 plus 1 over 2, or n plus 2 over 2, right? Does that make sense? That's what we're trying to prove. So this is where I said, like, we're kind of get a little bit meta here. How do you think I can do some legal, logical manipulations to this and get there? And this is where the very small amount of thinking that we have to do comes in. What's that?
Multiply 2.
Okay, if I multiply by 2 on both sides, that is a legal move, and it would change things, but that's not the one that I want to do. Okay, and I'm not going to say that won't work, because you might have another way that totally works, but that's not something I want to do. Yeah.
Can you just replace all n with n plus 1?
Okay, and that was my trap. Yes, if I just replace all the n's with n plus 1, I have stated P of n plus 1. And that's what a lot of people end up doing, is they state P of n, they do a change of variables, and then they state P of n plus 1. Okay, this is the inductive hypothesis. That is, I'm assuming this is true. So now, I don't care whether this is true or false, really, at this point. I just say, well, if this is true, does it imply that the next one is true? So I want to show a logical link. And there's great temptation to do just a simple, like a U substitution in calculus, if you've seen that, or a change of variables, if you've seen that. And you're still writing down something that could be useful, but it's not this. It's not this link. So I'm glad that I'm setting you up for that. So somebody's got to say that, okay? All right? Both good answers, guys. This is what I want, is just creative answers. What can we do to both sides? What's something we can do to both sides? I can pop my knee and my foot. I could add something to both sides. Jordan says I could add 1 to both sides. I agree, I could add 1 to both sides. However, let's suppose I add 1 to both sides. I'd have the sum as j goes from 1 to n of j plus 1 equals n times n plus 1 over 2 plus 1. Not quite. Yeah. Do you have your hand up?
No.
Is your name John?
Nope.
Crap.
Aaron.
Aaron. What's your last name?
Hinkley?
Hinkley. I was going to say, is it Hinky? Because I was just talking Jordan Stickley. Gosh darn. Yeah, Mike.
Add 2?
Add 2, closer. I like where you're going. What's another number that I could add to both sides that might help out? Yeah, Ming Ching.
And n plus 1 for both sides.
I'm going to add n plus 1 to both sides. All right. J equals 1 to n of j plus the quantity n plus 1. Now I can't just add n plus 1 to one side. I have to add it to both sides, right? Because that would be rude. So I'm going to add n plus 1 to both sides. So this is n times n plus 1 over 2 plus the quantity n plus 1. Now we're going to deal with the magic of summation notation. Click OK to continue working. I'm working really hard. I'm working really hard. I really like having a clock up here that works. Don't shut off. Okay, the magic of summation notation. This, as you'll recall, is the numbers 1 plus, is the sum 1 plus 2 plus 3 plus 4, etc. plus n minus 1 plus n. So that makes this thing, this whole thing, now the sum as j goes from 1 to n plus 1 of j. Let's talk about that for 2 seconds. Suppose you were like, Steven, I really want to sum the numbers 1 to 6. and I said, okay, let's do it together. And we stand here like this, and I say 1 plus 2 plus 3 plus 4 plus 5, and then you jump up and down and say, plus 6! Yay! We've just summed the numbers 1 to 6. All right? Is that the creepiest mathematical thing you've ever heard in your life? I hope so. I sum the numbers 1 to 5 and then add 6. I've summed the numbers 1 to 6. Have you ever heard anything more mind-boggling than that in your life? Probably not, let's face it. Okay, but 6 and 5 are not special. This is the sum of the numbers 1 to n. 1 plus 2 plus 3 plus ... plus n. And if I add n plus 1 to that, I'm summing the numbers from 1 to n plus 1. If this doesn't make sense, use your powers of reviewing to look over your summation notation stuff from earlier in the semester. Okay? And even if this does make sense, you might want to go back over that. All right, great, Steve. That's awesome. We got the left-hand side, but what is this garbage on the right-hand side? Hold on. Let's do some science. If we're calm, we can treat this as 2 times n plus 1 over 2. This is n times n plus 1 over 2 plus 2 times n plus 1 over 2. Just be calm. So a lot of what we've got in the mathematics education is if you see something that looks like it might be an answer, you know, pounce on it and attack it with your teeth and your claws, right? And it's not, you know, think about maybe how to trap it into a box so you can torture it and then, like, you know, let it feed you for years and years by drinking its milk. So, I don't know. You guys are weird. Okay?
What are you going about?
I'm going on about a lot of people will get to here and say, well, that doesn't look immediately like the answer. If you have a little bit of patience and you manipulate things